In Bose-Einstein statistics, today we are going to deal with a very important problem, and this is regarding the superfluidity. Actually, in this lecture, we will find the criteria under which a liquid will behave as a superfluid, particularly in case of the liquid helium-2. What will be the criteria when this liquid will behave as a superfluid and it will not behave as a superfluid? Actually, you have studied in the previous lectures that Landau assumed two types of excitations, and you have also seen that at low momentum the excitations are phonons or quantized sound wave. But as the momentum increases, we get another type of excitation, which is quantized classical vortex motion, and that is called Rotons. Okay. Actually, when the number of phonons and Rotons is not very large, then the liquid helium can be regarded as a mixture of two ideal gases, a phonon gas and a Roton gas. Actually, these two excitations are assumed to be two parts of one and the same excitation energy momentum curve, which I have shown in this figure. Okay. It is clear from this energy momentum curve that it first rises linearly. You can see this linear part of the curve, and this is due to the phonons. And this reaches to a maximum, and then you can see it falls to a minimum at momentum P naught, which I have marked here. And after that it again rises. Okay. Actually, in thermal equilibrium, the regions near the minima of this energy versus momentum curve are of particular importance. Okay. This superfluidity, is actually the consequence of this energy momentum curve. So we have mentioned it here. You can see that superfluidity of liquid helium-2 is a consequence of the properties of energy spectrum, okay, which I have shown just now. You know that helium-2 is a quantum liquid, and its energy spectrum is represented like this. You have seen these facts in the previous lectures, that energy at momentum P is given by Cp for phonons, okay, and this energy for Rotons is given as delta plus P minus P naught whole square divided by 2 mu. Actually, here this delta, you can see this represents the minimum energy of this Roton, and I have marked it here. You can see, okay, when momentum is P naught. And at any momentum P, this energy will be delta plus P minus P naught whole square divided by 2 mu. Okay. Actually, this helium-4, He4, displays a superfluidity below the critical temperature. Okay. In fact, at 0 Kelvin temperature, the entire liquid you have studied in the previous lecture is in its superfluid phase, that is, it is in its ground state. Okay. Now, let us consider, to deal with the problem of superfluidity, a large volume of the liquid which is flowing through a narrow capillary tube without exhibiting viscosity. Okay. So if you consider that there is a large volume of liquid at absolute zero temperature, through which a solid is moving. Here I have shown that there is a solid sphere. This may be of any shape, but I have shown in this figure that this is a solid sphere and it is moving through this liquid, and the temperature is maintained at 0 Kelvin. Okay. So when in this large volume of liquid a solid moves, then in case of normal fluid, viscous force F, which I have marked it here, you can see, acts on the body, and this opposes the motion of the body. If V is the velocity of the body in rightward direction, the viscous force F acts in the leftward direction, because this is just a force of resistance. It opposes the relative motion of the solid with respect to the liquid. Okay. In fact, as viscous force opposes the motion of the solid, so definitely work will be done against this viscous force, and this work done is transferred to the liquid in the form of heat energy. Okay. And as the liquid is heated due to transfer of this energy from this solid to liquid, the state of lower energy of this fluid will change to that of higher energy. Okay. And this process will create an elementary excitations in the fluid. In fact, Landau shows that such excitations are impossible in liquid helium-2. It is not possible in liquid helium-2 as it is possible in ordinary liquid, but it is not such excitations are not possible in liquid helium-2 due to the shape of the energy spectrum which you have seen just now. Okay. All these things which I have just explained, I have mentioned here for your convenience. I have written all those facts so that it will be more convenient to understand this video and writing in your examination. Okay. Now actually we are now going to find theoretically the criteria for superfluidity, and for this let us consider that the liquid contains no excitations in the beginning, and when a body starts moving through the liquid, it creates some excitations. Okay. But before the motion of the solid in the liquid, there were no excitation, but when the body starts to move through the liquid, some excitations are created. We consider it. Okay. Now we consider that this N of P, this N of P is the number of excitations with momentum P and energy E of P. Okay. In fact, in that condition, the increase in energy of the liquid will be what? As you know that this E of P represents the energy of all those excitations whose number is equal to NP. So the energy of this NP excitations will be NP times EP. And when we will sum up all these values for all values of P, then we will actually get the total change in energy. So the total change in energy of the liquid, which is given by delta EL, that is given by summation over P NP times EP. Okay. And similarly, if you want to calculate increase in momentum of this liquid, what will be that? That will be delta PL equal to summation over P NP times P, because P is momentum of each excitations having the number of excitations having momentum P is NP, and so for all values of P, this will be summation over P NP times P. Okay. Now let us consider these two results have been written actually for liquid. This delta EL represents the change in energy of the liquid and delta PL represents change in momentum of the liquid. Okay. But now we have to calculate what will be the change in energy and change in momentum of the body or the solid body which is moving through the liquid. And for this, let us consider that this Pi represents the initial momentum of the body and this Pf represents its final momentum. Okay. So if Pi and Pf are the initial and final momenta of the body, then increase in energy of the body will be what? Actually, the body has kinetic energy, and you know that kinetic energy is given simply by P square divided by 2m. So we will simply subtract the initial energy from the final energy of the body, and then we will get the change in energy of the body. So delta EB, which represents the change in energy of the body, what will be that? That will be simply Pf square over 2m minus Pi square over 2m. Here actually m is mass of the body. Okay. And equivalently you can write it as Pf square minus Pi square divided by 2m. So this is the change in energy of the body. Now, since the initial momentum of the body is Pi and its final momentum is Pf, so simply the change in momentum of the body will be Pf minus Pi. Okay. Now see this equation 3. This equation 3 can be simplified in this manner. This delta EB is given by, since it is Pf square minus Pi square divided by 2m. So this Pf square minus Pi square can be written as Pf plus Pi in vector form dot Pf minus Pi. Okay. Because you know that a square of a vector is simply the scalar product of the vector with same vector. Okay. So this can be written like this. Okay. Now when you will simplify this, what will be your result? You can see from here as delta PB is equal to Pf minus Pi. So if our aim is to eliminate this Pf in terms of Pi, what will be this? You can see that this Pf can be given by Pf will be Pi plus delta Pb. Okay, plus delta Pb. So instead of this Pf, you can write Pi plus delta Pb. Okay, and here is plus Pi, so this will be 2 Pi plus delta Pb, and Pf minus Pi, you can see equation 4, this is simply delta Pb. Okay, so this expression becomes 2 Pi plus delta Pb dot delta Pb divided by 2m. Okay, and we will further simplify this result to some extent. So you can see we can write this as 2 Pi dot delta Pb over 2m plus delta Pb square over 2m, because delta Pb dot delta Pb, this will be delta Pb square. Okay. Now as you know that this Pi divided by m, Pi divided, here this 2 and this 2 will cancel out, and Pi divided by m, this will be the initial velocity Vi, because momentum is mass times velocity. Okay. So this first term will become Vi dot delta Pb plus delta Pb square over 2m. Okay. So delta Eb is in a simplified form given by Vi dot delta Pb plus delta Pb square over 2m. Okay. Now see equation number 1 and 2 here. Equation 1 reads like this you can see, and this is your equation 2. So this from these two equations, if you want to write this delta EL in terms of the momentum P, we can simply multiply this equation 1 by P and also divide by P, but P is a vector, so we have to take the modulus of that. Okay, and when you will take the minimum value of EP divided by P, then delta EL will be definitely either greater or equal to that much. So from these two equations you can write that this delta EL is greater or equal to summation over P NP times mod of P times mod of EP by P minimum. Since here this EP by P minimum is the minimum value of the ratio of EP by P, so here the sign of inequality has been used. Okay, you can see that this P and P will cancel out, and the terms remain will be NP times EP. Okay, but as we are taking the minimum value of the ratio of EP by P, so here the sign of inequality exists. Okay, now as this summation over NP times mod of P, this will be according to equation 2 mod of delta PL. Okay, you can see this equation number 2 here, that this delta PL is simply summation over P NP times P. So when you will take the modulus, then it will be mod of delta PL. Okay, so you can see that this delta EL can be given as it is greater or equal to mod of delta PL times EP mod of EP by P minimum. Okay, now we assume that energy and momentum are conserved in this transition in which excitations are created in the liquid. And as the energy and momentum remains conserved, so definitely the change in energy of the liquid will be equal to change in energy of the body, and the change in momentum of the liquid will be equal to change in momentum of the body. Okay, when energy of liquid will increase, the energy of the liquid will increase, then the energy of body will decrease. Okay, and both must be same for the conservation of energy, and similarly for the conservation of momentum, increase in momentum of liquid must be equal to decrease in momentum of the body. So from these two conservation principle, you can write that this delta EL must be equal to delta EB, and similarly delta PL must be equal to delta PB, because delta EL represents the change in energy of the liquid and delta EB that of body. Okay, now we will substitute these equations 5 and 6 in equation 7a. This is your equation 7a, and we will make the use of equation this 7b here. So you can see that equation 5, this is your equation 5. Okay, at the place of delta EB, you can write this VI dot delta PB plus delta PB square over 2m. Okay, and so I have written here at the place of that. Okay, and that is equal greater or equal to delta mod of delta PL times mod of EP by P minimum. Okay, now you can see that this delta PL is a common factor. Okay, you know that this change in momentum I have assumed here is in the direction of this VI. So if you assume that VI and delta PL are in the same direction, then this VI dot delta PL, this will be simply equal to VI times delta PL. But if we consider that both are in the same direction, okay, then this delta PL is a common factor, and so we can cancel it, and the remaining terms will be what? That will be VI plus mod of delta PL over 2m, and that is greater or equal to, here this delta PL will cancel out, and that will be greater or equal to mod of EP by P minimum. Okay. Now this delta PL divided by 2m, what will be this? You know that this is actually the modulus, so this will be in fact delta PL divided by 2m, and so this will be actually equal to m times Vf minus Vi. This is actually the change in momentum, and divided by 2m. Okay, so this m and m will cancel out, and the remaining terms are Vf by 2 minus Vi by 2. Okay, now this Vi minus Vi by 2, this will be simply Vi by 2, and so this will be Vi plus Vf divided by 2, which you can write this just as an average value of the velocity, which is V. Okay, so we can write this like this. This is Vi plus Vf divided by 2, and which is greater or equal to EP divided by P minimum. Okay, and actually, as I have told you, that this Vi plus Vf can be treated like the mean value of velocity, and so you can write that this V is greater or equal to modulus of EP divided by P minimum. Okay, minimum. Actually, this inequality condition must be satisfied for the creation of elementary excitations. When this will be satisfied, only elementary excitations will be created. And so you can see that if this Vi is less than EP divided by P minimum, then there will be no excitation in the liquid, and hence there will be no excitations, and the liquid will be in the superfluid phase. Okay. Actually, this equation which we have obtained is known as the Landau criteria for superfluidity. Okay, this is Landau criteria. Actually, in this regard, we define a very important value of velocity, which is called critical velocity, and that is denoted by the symbol Vc. And this Vc is just when you will take the equality sign, you will get the a proper value of velocity, which is called critical velocity, and so it is given by mod of EP divided by P. Okay. Actually, this critical velocity plays a very important role in the discussion of superfluidity. This actually limits, this actually indicates the upper limit on the velocity of flow up to which the liquid exhibits the superfluid behavior. It means if the velocity of flow is less than this critical velocity Vc, then the liquid will behave as a superfluid. But whenever velocity is greater than this Vc, the superfluid behavior vanishes. Okay. So this is a very important value of velocity. This is just like you have studied in case of viscosity, the critical velocity for the motion of flow to be steady and or streamline and turbulent. When the velocity of flow is less than critical velocity, then the velocity is actually streamline, and after that it becomes turbulent. Similarly, you can say here that when the velocity of flow of fluid is less than this critical velocity or up to this critical velocity, only then the fluid behaves like a superfluid. Only then it displays superfluid behavior. But whenever velocity of flow becomes greater than this Vc, then its superfluid behavior vanishes. So we simply say that this is the upper limit on the velocity of flow up to which the liquid exhibits superfluid behavior. Okay. Now, if we consider that liquid has a particle-like spectrum with energy EP equal to P square by 2m, then what will happen? Actually, before this point, we have considered that EP is not equal to P square by 2m. You know that this P square by 2m is simply the kinetic energy or the non-relativistic kinetic energy of a particle. Okay. But before that, we have considered in case of phonon and roton that expression of EP is different from this. Okay. But if we consider that liquid has a particle-like expression for energy or particle-like energy spectrum, then EP will be given by P square by 2m. And in that condition, this Vc will be equal to what? That will be EP divided by P minimum. And you know that EP by P will be equal to what? EP by P will be equal to P divided by 2m. And the minimum value of this P will be equal to 0. So in this condition, when you will find the minimum value of EP by P, that will be simply equal to 0. Actually, such a system cannot be a superfluid. Okay, that cannot be a superfluid. Okay, and thus an ideal Bose gas which undergoes Bose-Einstein condensation cannot display superfluidity. Okay, in the ground state, when the ideal Bose gas is in ground state, that completely behaves like a particle or a super atom, and it has no in fact energy. Its energy is 0. So in that condition, we can say that in the condensed phase or the Bose-Einstein in case of Bose-Einstein condensate, the liquid behaves like a particle-like spectrum and it cannot display superfluidity. Okay. So, however, liquid with energy spectrum EP, okay, EP means which I have shown in the energy spectrum curve. If energy is like that, what will happen? You can see that for EP, for which Vc is greater than 0, actually then it will exhibit the phenomenon of superfluidity. Okay. So now after knowing the criteria for superfluidity, you have seen that for the superfluid behavior, this Vc should be less V should be less or equal to Vc. Only then the liquid will behave like a superfluid. But when this V will be greater than Vc, this superfluid behavior vanishes. So this critical velocity determines the upper limit for the superfluid behavior. Now, as a particular example, let us consider the case of liquid helium-2. Okay, and as you know, in case of liquid helium-2, there are two types of excitations, and those are phonons and rotons. Okay, and you have seen that for phonons, this EP is equal to Cp. Okay, and so if you want to calculate the critical velocity for this phonon gas, what will be that? This Vc, as you know, this is given by E mod of EP divided by P minimum. And since EP is equal to Cp, so EP by P will be simply equal to C. And C, you know, this is velocity of sound. And this velocity of sound is 240 meter per second. Okay. So critical velocity in case of phonon gas is 240 meter per second. Okay. Now, if your aim is to find the critical velocity Vc for Rotons, then you have to find the value of this EP divided by P minimum for Rotons. As you know that in case of Roton, the energy is given by what? You have seen earlier that this EP in case of Roton is given by delta plus P minus P naught square divided by 2 mu. So in this case, this EP divided by P will be what? This will be delta by P plus P minus P naught whole square divided by 2 mu P. But to get the value of this Vc, we will have to find the minimum value of this ratio. Okay. And when your aim is to find the minimum value of this ratio, you know this EP by P will be minimum when its derivative will be 0. Okay. So we will simply differentiate this RHS with respect to P, okay, and equate to 0 to get its minimum value. That is what will be the value of momentum P for which this ratio EP by P will be minimum. And for getting that value of P, you have to differentiate this RHS of equation 13 with respect to P and equate to 0. So let us see here. For this, del P EP by P must be equal to 0. Actually, I have not differentiated, I have not done the algebra here. When you will try it to differentiate and equate to 0, you can do it. This is just a homework for you. You will get the result P square equal to P naught square plus 2 mu delta. It means when the momentum P is equal to square root of P naught square plus 2 mu delta, actually in that condition, the ratio EP divided by P will be minimum. This will be actually minimum when P is equal to this much. Okay. So for getting the value of this Vc in this expression EP divided by P minimum, you have to replace this P by this value which I have defined in equation 14. Okay. So you can see that this EP by P is given by this expression defined in equation 13, and in this expression now at the place of P we will write simply this expression root over P naught square plus 2 mu delta. So it will be P square minus P minus P naught whole square. But at the place of P, you can see I have written P naught square plus 2 mu delta to the power half and minus P naught and the whole square. And divided by 2 mu P. Again at the place of P, I have written a square root of P naught square plus 2 mu delta. And plus delta divided by P. So at the place of P, again you can see this is root over mu, P naught square plus 2 mu delta. Actually here this 2 mu delta, this is much smaller than this P naught square. So we can neglect this 2 mu delta here for an approximation. Okay. So when you will neglect this 2 mu delta, you can see that this first term, after neglecting this 2 mu delta, this first term will become simply P naught minus P naught divided by 2 mu P naught, and P naught minus P naught will be 0. So this first term will become 0. and only the second term will remain, and here we will again neglect this 2 mu delta. So this will be approximately equal to simply delta divided by P naught. So I have written here that this Vc is approximately equal to delta divided by P naught after neglecting this 2 mu delta with respect to P naught square. Okay. And when you will put the value of this delta divided by this P naught, actually in that condition you will get that this Vc is almost equal to 63 meter per second. So you can see that this is the critical value of velocity for the superfluid behavior. This is the upper limit. So we can conclude that the liquid helium-2 exhibits superfluidity if the velocity of flow is less than about 63 meter per second. Okay, and this is actually the case of Rotons. Okay, actually the theoretical value of this Vc is large in comparison to the experimental value. In this case, no phonons or Rotons can be created. At non-zero temperature, where there already exists some phonons and Rotons, new phonons and Rotons cannot be created owing to the motion of liquid helium. And at non-zero temperature, when the walls of the vessel are in motion, a part of the mass of the liquid helium will behave as a normal fluid, and the other part will behave as a superfluid having no viscosity. Okay? Actually, there is no friction between these two parts of the liquid moving through each other, and thus we may regard the liquid helium as a mixture of two fluids, superfluid and normal fluid. Okay? So I think you have understand the criteria for this superfluidity, particularly in case of liquid helium. You can see that this liquid helium-2 exhibits superfluid behavior only when the velocity of flow is less than about 63 meter per second. Above this value of velocity, this liquid helium will behave as a normal fluid, not as a superfluid. Okay? So this was all about the superfluidity, and this is a very important concept for your examination. So watch the video seriously, write down all these things in your notebook and revise it. You will get the complete concept of this superfluidity after that. Okay, thank you very much.